So welcome to this plenary session. This plenary session designed for damage control and structures. To me, this is going to go to the heart of the matter. I'm really looking forward to these presentations. We have quite an international group of 6 speakers, a couple of Italian Kiwis in there dominating it. I've asked them all to sit up here so that they can't get away. So the first 4 presentations will be a maximum of 20 minutes each, and the last 2 10 minutes each. And I would like them to keep to time so that we can, if my arithmetic is right for this session, that will leave us 15 minutes to have some discussion and perhaps answer some questions about this topic. So please think up some questions that you can offer at the end. We have a couple of starters already lined up. We'll make a start, and the test of how this is going to work will be, the scene will be set by the first speaker, Professor Pampanin. I'm a bit worried. I know how many slides he's got, and he's going to have to go fast. So Stefano Pampanin's topic is toward the ultimate earthquake-proof building, enhancing resilience through an integrated low-damage building system, and I think this is a very important subject. There may be a question on this at the end. Stefano, please.
Thank you, Mr. Chairman. Thank you, David, and everyone for being here. So I'm not going to break my record. It's only 3 slides per minute. Now, to try to enter right away into the core of the presentation, for the non-locals or people who have not been in Christchurch before the earthquake, that was Christchurch City before the earthquake. This is Christchurch City during the earthquake, and this is Christchurch detailing after the earthquake. The one that we are going to, we all technical engineers said, what a fantastic plastic hinge. It looks like a Park and Poly Priestley book. Before taking off the ceilings, after taking off the ceilings, this is the PricewaterhouseCoopers building, 22-story building, 1980. I've been literally using this slide for probably 15 years to show how fantastic the precast concrete solutions in New Zealand are when compared to somewhere else in the world, including Italy, where precast concrete is only precasted. It's not a mixture between precast and emulation of cast in place, while in New Zealand, Japan, and other countries, you get actually a mixture of that. So the emulation of cast in place means that you get an emulation of cast in place behavior in the connection, which means that you get a plastic hinge. Is exactly what you wanted to have because it's part of the capacity design consideration. And then as a result of that, you just end up having a building which has to be demolished. Now, in a way, we knew that. From a technical point of view, as we know, the engineers in New Zealand has been a bit hammered by or blamed by the population, saying you did not do your job, you are incapable. It was quite a harsh time with a commission of inquiry, trying to ask why not things did not work well. And we know that the answer from a technical point of view is that actually did do the job of saving lives. So we are repeating things that we know very well. Very quick question, how many engineers are in the room and scientists? So technical people, let's say. Or let's say quickly, how many are not engineers in the room? Politicians, insurer? I want to see some insurer here. Thank you very much. Fantastic, you are there. Real estate? No one? Okay, sometimes the problem, and today is the same thing, is that we are preaching to the converted, and we are saying that great job, done deal. So typically with a car, you would go to your insurer, get keys in your hand, and you just run with a new car afterwards. In this case, it didn't work. Now, showing the SEER video of the city before and after, when I do it overseas, people are shocked. They are saying, but New Zealand is supposed to be a well-developed, non-corrupted, well-aware seismic country, where things, even in a big earthquake, should not be like that. And even worse, when I was explaining that from the area point of view, the city of Christchurch after the earthquake looked like something like Middle East, Dubai, under deconstruction city instead of being in construction. So quite a substantial result, which is questioning now, is becoming probably the most of interest earthquake in the world, because people are taking New Zealand as a model. They were, and they're still, in the sense that it's a well-developed, well-aware country in terms of seismic resilience, seismic resistance. How could it possibly lose potentially 40 billion New Zealand dollars, which means 25% of the GDP, which means we had the Minister Joyce explaining that it meant actually 20% of depth of the PIL, 20% of the GDP increased in terms of depth. Now, we were thinking about doing something okay. Now people are asking us, the population, society, to do safer and resilient. Resilient is something which is hiding everything. As Gianmari was mentioning, the mayonnaise for a cook is actually, can be an important term, but very, very complicated. So what does it mean, resilience? If we borrow the concept, and that's been happening from other disciplines, resilience is the capacity to be hammered, in a way, to be impacted by an event, and then coming back, resurging back, but not in the elastic range. From our technical point of view, elastic would be to come back through the same path. It's not the same thing. We got hammered and we are recovering, and the importance would be, first of all, to try to recover quick, not too quick, otherwise you get a mistake, but try to recover quite promptly, let's say. But remember that if the economy was booming, what we have to recover back is actually back there. And yet, we have been having quite a disruption in our lives, which we would have liked not to have. So this is what we are trying to explain to the non-technical people about our contract. I'm the engineer, I'm designing for you something like that. I wish that we were using all the same slides, which is I'm designing a seismic resistant building, which is going to have a fantastic plastic hinge in the beam column joint, and it's going to be, the skeleton of your building is going to be damaged, but where you want it. So it's like having your knee being severely damaged, but you're still standing. Your hips or your diaphragm are completely gone because rigid diaphragm assumptions from an ETABS or sub 2000 code doesn't stand, so they're not really working in the rigid length. Of course, the non-structural element, heavy or not heavy, are going to be completely destroyed at a seismic design level, so 500 years design. And if you're looking at the facade, so the envelope of the building, unfortunately, there's something which is actually a problem around the world, because these are supposed to be non-structural, but they can be in trouble, getting into a drift level, and they can make them falling apart and becoming life-threatening. If they are life-threatening, so theoretically, they should be able to stay there intact without collapsing under the design level of earthquake. No code in the world is actually implementing it, but every code in the world is talking about life safety. So we keep talking with our people. Sorry, keep going behind. And this is just a superstructure, but then your foot are in trouble. So this will be what we hope Misko will give us some solutions, because it's not only the superstructure, but it's also the foundation. So it's the whole building system. And we've been mentioning a lot about low damage and what low damage means and doesn't mean. At least it should mean that the structure should be okay. Then should mean that the non-structural, the dress of the building, which is very expensive, should be okay. And then it should mean that, of course, the foundation should be okay. And the whole community with the vertical infrastructure and horizontal infrastructure should be okay. So in a way, we've been, I shouldn't say cheated, but we haven't said the truth to the population when we should be explaining that you design for that by code everywhere in the world, that's what you get, red tag. And if you want to know more about that red tag, this means it's an add-on to the Vision 2000 document, repairable, irreparable. We don't really know where the line in the sand stands, but we know that around here, more likely you're not going to be repaired. So you don't get a new car unless you have an insurance, but you are not able to restore your life very promptly. Same tagging system on something that we as an engineer understand. Structural engineer, think about a pushover. How many of us would have still a friend in our client when you go there and say, that's exactly what I designed for you. And I'm a fantastic engineer because I'm giving you a great solution. It's going to be a seismic design system. And so what is the problem? We have been not explaining to the normal non-technical people that a code doesn't mean target. A code is a minimum by law, something that very often I mention to my students. A code is what you have to follow if you want to avoid jail, nothing more than that. Now, it's not meaning a good design. So we are talking about earthquake resistant, and people are thinking earthquake proof. It's not an earthquake proof. It's not a bulletproof, come and shoot me. And this is what people think that an earthquake resistant design is. So there is a major communication of risk that we are not delivering, and we should be doing more. So in a way, what we should be doing is to take this basic objective and pushing it back and making something whereby under quite a significant earthquake, I'm still in the good operational range. Aurelia Lagos was mentioning, people would like to have immediate occupancy after an earthquake. And that's exactly what they would like to have. If the earthquake is very big, fair enough, at least give me a repairable solution. If it's huge, fair enough, still I want to have a repairable solution. Now, let's go back. Learning from our ancestors. We did not invent earthquakes. They've been there for a while. And we did not invent earthquake-resistant structure. They've been there for a while. And one of the oldest possible way of taking earthquakes and going through that is rocking marble blocks on the top of marble blocks. No steel, no dissipation devices, no post-tensioning, no nothing. It was really the concept of blocks moving against each other and getting the mass behaving as a weight and give you stability. The mass is bad, weight is good. Can we have something which gives you only a weight, but not a mass? We should be basically taking off gravity in one direction and not in the other. Gianmario mentioned that we like to go back and see that not only the Greek or that type of system was providing a rocking behavior, but also they were having something which was, this is a very bad broken English translation of the Latin of the Pliny the Elder. Diana Temple was using charcoal spheres as well as wool furs, sort of a slider, in addition to the rocking system. Fantastic. They were extremely ahead. There are other concepts and so forth. Base isolation is not being invented by B.R. Robinson, but B.R. Robinson has provided one of the most used system that has been really leading the world in terms of isolation, lead rubber bearing. If you think about the other one, sort of a slider type of solution, that was already the charcoal and the wool furs, but the Greek did not have a patent. I thought that this was one of the earliest. Gianmario proved me wrong, saying that the French, where is Caroline? Caroline. We can't give credit to the French to have been inventing the first patent. So I think that Viscardini, Italy, deserves to be referred as the one on that. Caroline, sorry for that, and Tony Holden. So what are we doing? Is basically nowadays is re-engineering the past, re-engineering what solutions of isolation, rocking, in a way that people have been already be using, and try to add something more. So the new system is basically a new temple, which instead of going through back and forth and getting the damage in the ductile plastic hinge, is actually jointed, is ductile, is a temple rocking, is not made of marble, is made of concrete, steel, or timber, whatever material we want to use, glass, anything possible, and is taking advantage of a recentering massless weight. What is a massless weight? A cable, a tie-down. A tie-down is something that can give you stability, weight, but not the mass of the temple. So it's basically, and don't call it post-tensioning, call it a tie-down. Everyone will understand a rope. While it's moving back and forth now, we have the option, which they did not have in the past, to use dissipation. What type? Easy, mild steel bar. But if we want to move one step further, we have to think that the same, very often people have been trying to say, imply that capacity design has been proved wrong by the earthquake. In reality, I'm saying that capacity design has been saving a lot of the concept of, has been saving thousands of people, possibly in Christchurch, possibly, not meaning around the world, not just think about around the world. But capacity design is still extremely valid because itself, if you remember, it was nothing else, which is nothing else, than the concept of the chain. And we are still applying capacity design, and we must apply capacity design in any single possible new connection or new system in the future, where for us capacity design is the whole building system. Starting from the foundation, moving up, skeleton, non-structural element, horizontal, vertical, so it's the whole concept should be still maintained. If in the past, pre-70, we were at this level, and after we got to the weak beam strong column mechanism, capacity design, the fact that a plastic hinge meant damage, it was not a capacity design issue. It was a technology issue. Lack of technology, not available until a few years ago, implied that a plastic hinge means damage. Now we have the opportunity with the 2,005 years old technology, the Greek temples, to have a plastic hinge not meaning damage anymore. But yet, if we have steel rebars within our connection, we are going to have a not easily repairable system. So how can we get the repairability of the weakest link of the chain? Now let's think about, for example, concrete in a different way. Instead of having the steel inside the concrete, let's put at the connection level the steel outside. And this steel outside, if properly protected by corrosion, and if properly arranged to have an anti-buckling behavior, is basically the fuse, the electrical fuse of our seismic system. It's our seismic fuse. It is a capacity design implementation. We like to call this plug and play. Why? Because if you give a name, people typically remember and they like it, becomes fashion, and they use it. And this has been one of the success of this concept. Now, just imagine, think about communication of risk, that instead of talking to our client, our friends, about damaged plastic hinge, we should be talking more about what type of viscous temper or shape memory alloys or device 2.0 do you have in your living room. So if we, that was a joke in 2005, if we make earthquake engineering becoming fashion, now we have the possibility of actually getting things happening much quicker and faster. You can do it in concrete, you can do it in steel, you can do it in timber, and the whole things can be developed once you get the concept. Obviously, details have to be occurred in a different ways, so things have been R&D, research and development, happening quite quickly in the last 12, 15 years. And this is only about component, and then frame and walls. Then you have to address the flooring system. There's been a humongous effort starting definitely in New Zealand, a lot of contribution. Des Bulls, Baby, in a way, pushing for diaphragm and solutions. There are different options that nowadays we can implement, a non-tearing flooring solution, what forth. What I'm saying is put everything together. And then don't remember that the dress, being an Italian, you would appreciate that we care about that. And the architecture, that's what I like in the Italian, my half-life over there, is that the architects are quite demanding in terms of asking, fair enough, whatever you give, but come on, I want to have still maintain the energy efficiency of the building and the whole architectural beauty and what forth. So what we are getting is that if we could think about a skin, having a skin which is going around our skeleton and being able to have a waterproof skin, which is deformable but not damageable, basically what we are doing is think about getting the skin divided in very many small pieces, which is what in some animal furs you get. So many small pieces which are moving against each other slightly, and that movement against each other, either for partitions or for facades, is actually allowing the movement to happen. We have been developing this system, they are existing, they can be adopted, and they have been already in some situations, as a low damage, we are not saying non-damage, they can get, for clay bricks, for partitions, or for facade, to 2.5% of drift without a single crack, so quite substantial. And the whole concept is allowing this small rocky movement of the Greek temples within the system. Now let's see how it does it look like. So to our client, we should say, forget about the old generation of buildings. Now we have a new generation of buildings, which is made of a skeleton, which likely is going to be repairable, is made of flooring system, which are repairable, is made of a dress, which is more likely repairable or let's say less damageable, and so forth. If you put the package together, you're getting towards that earthquake-proof. We're not having the earthquake-proof building as yet. Gianmario spoiled the surprise, not the surprise. He was showing that isolation system using lifting a house will be the future. I mean, it's a concept. In reality, we are going to get ultimate proof building when we are going to be able to completely lift up our house or property when the earthquake comes, maybe using magnetic fields and so forth. So 15 years of research into a lab when the skeleton, the dressing is all together. I'm going to show you not the details, but the whole thing is together. And now, hold on, if it works, it's supposed to be working. Hold on, go back. Now this is supposed to start. Why it's not starting?
It's just delayed.
Okay. So this is basically a renewed rocking Greek temples, beam and column, post-tensioning through. You get the dissipators, the plug and play top and bottom, and these went through really literally 100 earthquakes before we allowed the press to come over and see what it looked like, because we did not want to have people, we say, bringing bad luck when you're doing research. And after they came over, we really told them, now shoot the earthquake that you want. We were having the table for the potential of the table, shooting earthquakes that they were happy to deal with. Obviously, the next question was, yeah, thank you very much, but you're going to damage the non-structural component. This is just an example of, excuse me, it's supposed to be going. This is the example of the rocking temples in action. So the modern version. There you are, 2 minutes, okay. So it's moving a lot. Just imagine this big opening over here typically would be diffused, spread in a plastic hinge, means a lot of cracks. The sum of those cracks are concentrated now in gap opening, and the plug and play, which can be made of anything, are actually working. And this, if you can make it work, and then I will be flying through, is the skeleton, the skin made in pieces. Focus over here if you can. There you are. You see a little bit of relative movement is allowing the system to take quite a big level of drift. And underneath, the connection can be using U-shaped flexure plate invented by Ivan Skinner in 1972, anything else. Now, quick and fast, because I have 1 minute and 20, probably Misko will be reminding us that the whole system is not only made of the superstructure. And the earthquake in Canterbury showed that there are issues of the soil structure interaction. The foundation suffered a lot. From a point of view of performance, from the point of view of geotechnical engineer, that's the pushover that they will be thinking more about. And so it is possible, we've been working on it, to make an integrated performance-based design where the superstructure, the foundation, and the envelope in terms of non-structural element can be accounted for. Vision 2050, New Zealand reconstruction, the blueprint, there's been a lot of happening, and there is a lot of this technology going on. You can go on site, and you might be going into some of these buildings, concrete, steel, concrete timber, and all the 9 yard. But the interesting part is that we don't want to use one technology only. If possible, we can combine base isolation and rocking, such that if something goes wrong, you actually have that solution. Santelmo, 3 slides. And, or in a possible rocking potentially, just not to have a plastic hinge and dissipation. And Felice Ponzo is going to show you what it looks like. Now, I want to finish with 3 challenging slides. In the future, we want to get into a system which we can actually monitor, but not from the old way of thinking. You would like to enter a car and knowing everything, and these are written in Italian on purpose because you will know what they mean. We should be having our building system telling us what is happening to the building system as it goes. And this has happened partly in one of these low damage systems, and the concept is to have safer, sustainable, smart, S3 design, where you're going to have a system which is supposed to be safer, sustainable, and smart, fully monitored, and can give you this solution. Last slide. Now, how much does it cost? Now, think about what has happened in the last few years. So 50, telephone, moved to something, a mobile phone was very expensive, and then eventually we got what we got. How much did it cost? At that time, divided by the salary, was quite expensive. At that time, when it came out, divided by the salary was less expensive. Now it's affordable by everyone. So similarly, now you understand the thing, you can think about the computer. You remember this IBM 1980? Hugely expensive, less expensive, everyone has one. Now, why we don't think that a building system, 1950, post capacity design, and rocking cannot be affordable? And that's a matter of people have been doing marketing on that, so no one is actually doing marketing on this. So we should be telling people that the cost in this case did not change dramatically, but the performance changed dramatically. So it's a matter really, last slide, not bad. It's a matter really of communicating what we are doing, and basically the challenge that we are facing is if we really want to have a full building system, which is the whole 9 yard, who is going to help us selling it? Because it's not our job to sell it, like people would be doing for computers or phones. So a challenge would be maybe we should be bringing, I just say a name, iPhone or Samsung or Huawei to buy the New Zealand IPs of the low damage technology and selling around the world on our behalf. Thank you.
It's 58 slides in 22 minutes. It's not pretty good going. Thank you very much, Stefano. Our next speaker is Professor Felice Ponzo from the University of Basilicata in Italy. And his topic is implementing low damage building technologies, an overview of research in Italy. Please.
Thank you, Mr. Chairman. Good afternoon to everybody. With this presentation, I will try to show you some research activities that we are carrying out in Italy, particularly in the University of Basilicata, regarding the passive approach to control the seismic vibrations of structure, mainly by isolation, energy dissipation systems, dissipating rocking mechanism following the presentation of the introduction of the Stefano Pampanin. the need to study this kind of application is due to the awareness that actual code, the traditional standard code, are not longer, cannot longer satisfy the traditional approach considered for seismic protection of buildings. I mean, it's not possible that way to consider the cost, the social cost associated to the damage that actual code, traditional code can consider. Then we are starting to study and consider the consequence due to the a new generation of buildings, as is the title of this kind of conference, and consider the application that we can do. We can apply on new buildings, but also on existing buildings, because it is a big problem in Italy. We have a lot of existing buildings, and then we need to study, to search a new solution to upgrade the safety, the capacity of this building, but in from an economic point of view, acceptable for the society. Then, as you can see in this picture, the number of applications in Italy is now increasing. The number is correlated to the earthquake, also the code, the standard code that is evolving in this last decades. And you can see that a big number of, a significant number of applications started after the central earthquake in Italy of 2009, starting with the Progetto Case that consider a big number of base isolated buildings. The application in Italy now is divided mainly in two kinds of application: the seismic base isolation, the energy dissipation. The seismic isolation is represent almost the 80% of application, but in any case also the energy dissipation application are increasing in the last year. It considers various typologies of devices, viscous dampers, viscous elastic dampers, and so on. Then we are now consider what is the future for this kind of application, but starting from the research. Our activities are developed in, within a big program, Italian program. This is the RELUIS project. Is a network of university laboratories of earthquake engineering that now involve more than 1,500 researchers all of Italy in almost all university that works in the field of seismic engineering. That network has some facilities for earthquake application. In our laboratories we have a testing machine for type test and factory production control test that is able to perform tests on several kinds of application. We can see you can see here some kind of test that we can perform. That kind of application allows to better understand the behavior of this kind of devices. But as this morning said Gianmario Benzoni, I think is now the moment to start a very strong collaboration between earthquake laboratories in order to better understand which is the behavior and how we can use this information in order to improve the behavior of the devices and then of the structure. Our activities, I said before, is mainly devoted to the study of the existing buildings, because there is a big problem in Italy. For that, we started with the application considering existing buildings designed with for only vertical load. And then we applied, in this case, some base isolation systems, several kinds of base isolation systems, in order to understand the the performances of this kind of devices. We used rubber, steel, friction bearings, and shape memory alloys-based bearings in order to evaluate also the ratio between performance and cost. We observed that, for example, almost all devices had the capacity to improve dramatically the behavior, so reducing the interstory drift under the low damage, under the damage for non-structural elements too. In this application, you can see other tests we performed on buildings designed for vertical load only, considering in this case also the application of infill panels in order to evaluate the damage on this kind of elements. Also in this case, we observed a very, very good behavior of the specimen in order to achieve some good performance with a very, very low drift value observed at the end of the test. In several tests, we used also in situ application, because after lab test, several kind of devices were applied in real buildings. So we performed some release tests. In this case, is a building in Basilicata, in Italy, south of Italy. We moved buildings using a special device. Then we released suddenly the building in order to verify the effectiveness of the device. We used three configuration: shape memory alloys, rubber, and mixed rubber and sliders in order to understand the difference. All the devices were able to reduce drastically the oscillation of the buildings. But in Italy, we have a lot of reinforced concrete building, but also a lot of masonry building. It is a big problem to protect this kind of a building. So we used also several kind of approaches. For example, in this picture, you can see a mixed approach using the CAM system. Is a cables narrow that produces some increasing on the resistance out of plane of the masonry, and also the base isolation using the rubber bearings, high damping rubber bearings, and we observed also that buildings designed for vertical load were able to overcome the very high ground acceleration. In this case, we used some lab tests in order to evaluate the behavior of double curvature friction pendulum. Is a device now in Italy with a very increasing number of applications. For that, we need to understand well which is the condition of functioning of this kind of test, considering also different kind of friction, high friction, low friction, and medium friction, to understand also which is the residual displacement. And we used several tests with real accelegrams and artificial ones in order to understand the capacity. Moreover, also using this kind of devices, we performed new in situ test. This is a building, an industrial building based on Sicily in Augusta. We performed also on the completed building the release test using a public test. In that case, a lot of people filled the test coming on site during the movement of the test. The results were very interesting because now in Italy we are applying this kind of risk test in order to verify the effectiveness of design, to verify the capacity of the isolated systems in order to verify the real damping, the modal shape and the frequencies, then the period, the correspondence between the real and the design period. In that case, we found very good agreement between design and experimental values. Changing kind of devices regarding the energy dissipation, we performed a lot of tests in order to understand the difference between several materials. We consider hysteretics, dampers, but also viscous and shape memory based alloy in order to understand also on existing building which is the real behavior. In that case, we used the lab test, but also in situ test realized in ex-Italsider Bagnoli industrial area near to Naples, where we used a real building, cut it, and then for each piece we used several different kind of devices in order to understand the behavior. In all cases, we found good capacity of the buildings in reducing the seismic vibration. In that case, we are observing another test performed in the University Basilicata lab, in which we performed the test considering 7 kind of devices. Were involved a lot of universities all in Italy within the RELUIS project, and we used hysteretic with steel, aluminium, viscous eccentrics based on the shape memory alloys, viscous dampers, and so on. One of the results, very interesting, of this kind of application was that the dissipating braces systems are very robust. Is an approach that allows to reach the good results, also changing the value of the characteristics, mechanical characteristics of the devices in a very wide range. We found that, for example, for hysteretic devices, changing of the plus or minus 50% the resistance, the results doesn't change. It is very, very robust as results. At the moment in Italy, there is an increasing number of real applications in Basilicata region. We have now almost 10 buildings, mainly school buildings, realized with this kind of application. Steel braces with, in this case, steel devices. You can see here some details of this kind of application. This is a school in Potenza city, and other school that certify also the capacity now of companies, but also of designers to consider this application and to design this kind of solution. Another kind of application that we studied is the DISCAM systems. Is very near to the concept of the press system. We used some dissipative element in the angle, as showed before Stefano. In this case, the dissipative elements are formed by the L-shaped steel, mild steel, and they dissipate energy in the rocky movement between beam and column. Moreover, there are some steel angles that are deputed to increase the capacity of the column and the beams, and also that some stirrups are cam narrows that are applied externally on the beams, and then they can improve the capacity, the shear capacity of the beams. In that case, we can invert, some cases, the mechanism of weak columns, just to improving the resistance through the joint devices. Then for existing buildings is a very, very effective mechanism. In this case, we used the frame realized consider only vertical load. We applied very strong motion in order to verify the capacity of this kind of system to protect buildings. At the end, I link with the presentation of Stefano. I will present experimentation we are carrying out in the University of Basilicata in collaboration with the University of Canterbury. We started using the system to verify the capacity of beam column joint to be applied also to the glulam. This different kind of solution for wooden structure, European, typically Italian and the European solution. And we applied the test using also the configuration in the I don't know if we can back, but okay. In the movie, you can see the movement of the steel elements during the rocking of the beam respect to the column. The capacity of the dissipation capacity is highlighted by this figure where you can see the blue line, the only post-tension effect due to the beam column behavior, and black line, the effect of the dissipation due to the steel angle. After that, we performed the dynamic test on the building, on the 3D buildings. In that case, we applied at the moment almost 150 destructive earthquake without any damage. So we demonstrate that the system is very, very strong, is very effective. The next step, this is some result in order to verify that the system is very good with the post-tension. There is some improvement of the behavior using the dissipation in terms of increasing of the capacity of displacement and the peak run acceleration as input for the building. The next step will be a new solution for in order to reduce the displacement for this kind of buildings, using, in that case, bracing systems with U-shaped steel elements mounted on top of the inverted braces. Now we are starting with this kind of application. The next June, I hope to have Stefano in University of Basilicata to to present the experimental results to the engineers in Basilicata. We can see here some picture of the work that are now in progress. Concluding, the experimental that we are carrying out in Basilicata are confirming that the effectiveness and robustness of this kind of strategies. I think now we need to change the design code. We need to change way to design, because it's not possible now to accept any damage or reducing. It's important to reduce the damage after an important earthquake. In Italy now we are starting with the Italian government is starting with a very interesting operation in terms of encouraging the use of low damage techniques by incentive the design with the so-called Sisma bonus. Is like an economic advantage that the designer, the owner, can be using this kind of system. Thank you for your attention.
Perfect timing. Thank you very much. So our third speaker is Professor Alessandro Palermo from the University of Canterbury. Alessandro, your topic is damage-resistant technologies for bridges, a natural pathway towards resilience-based design.
All right. Thank you, David, and good afternoon, everyone. So what I want to do is start basically giving a little bit of a view of what we've been done in the last 15 years. So, what I want you to remember is basically just 8 key things. So this is a countdown, starting from 8 going down to 0. And we'll basically start from item number 8. The first thing is actually, because being Italian, you tend to go longer. I want to do the acknowledgement first. At least I acknowledge everyone. And this is really, I see myself more a messenger of a wider group. And these are all young researchers, but also colleagues that I work with, starting with Stefano in 2003 when I came over as a postdoc. So let's talk about these items. So item number 8, so we have lessons learned from recent New Zealand earthquakes. And I want to go straight and talk about the Kakura earthquake, because we had a good presentation yesterday. We have a good overview. But what I want to point out, your attention on 2 case studies. And this one is the lower Mason bridge, where the bridge is very close to Waihau, where we had the epicenter of the earthquake. And this bridge sustained, there were 7 bars fractured out of 16. And the bridge obviously was very close to the collapse, and the bridge was repaired within 1 month, obviously within loss of functionality within the bridge. And this is the repairing, was a sort of concrete jacketing. Now we look at the Hawatiri River Bridge. This bridge is close to Blenheim, not far from Blenheim. And the bridge is interesting because it went through 2 major earthquakes. We have the Sedom earthquake in 2013, and they did jet grouting on the piers, as you can see at the top and the bottom. And then in 2000, with the Kakura earthquake, again, further damage. And this poses some question about the post-earthquake residual capacity. So what are we going to do, again, the grouting injection with this type of structure, or we need to think about how we can sustain, especially multiple events and long duration earthquakes. And I like to just think about the Lower Mason Bridge in 1986. And that period, I was a kid. I was watching Magnum PI and the Ferrari GTB, of course, being an Italian, I like Ferraris. And now I think about 2017. I say, okay, this is the new Ferrari, 458. It's totally different from the 308. And the Hawatiri River Bridge was designed in 2007. And this is actually the supposed Ferrari that we are currently using. So what we have to think about, we need to think about the ingredients for a perfect damage control recipe. And this is the item number 7. Now, we know that there are a set of damage-resistant technologies, and obviously we know about seismic isolation. Have been excellent presentations so far. We know that we can also use pure rocking, where we can either have a rocking of the foundation, or we can have stepping piers, and we have a beautiful example here in New Zealand, the Rangitiki River Bridge designed by Becca. Or alternatively, as you've already seen from Stefano, we can think about mechanized hinges, which have ability to be, they have self-centering capability, and we have the ability to replace the reinforcing after the earthquake. And I think for a bridge, this is a quite a good concept, because when you design those sort of connections, especially for a bridge engineer, it's exactly the same philosophy as designing a plastic hinge type bridge. And this is something that you've already seen with Stefano, so I should go very quickly. But that is basically a comparison between a monolithic and a new generation. And I want to point out again that with this new generation of systems, you tend to have one big crack happening, and you want to minimize the damage in the member. or alternative, you want to know how to repair it after the earthquake, because this is really the key thing that is still missing in our design codes. And these are details that I want to show you later with some testing that we have done. Now, what are the ingredients for the recipe? And I think there are four main aspects that we should really focus on. Control material strains. And this is obviously important for devices, the devices we're going to use. Or if we use internal bars, we can be thinking about the bonded bars internally and make sure that we know exactly what level of strain for given performance limits. And very importantly, also think about low cycle fatigue, especially if you think, and we know that we are here in New Zealand, we are going to have long duration earthquakes. This is very, very critical. The other recipe is, part of the recipe is minimize residual deformation. And this is very, very critical because, again, you want to have the structure be able to bounce back to the original position. And then the third ingredient is maximize repairability and minimize recovery time. And the fourth one is, especially for bridges, also be able to guarantee long-term seismic resilience, because bridges are exposed to harsh environments, and so we need to start thinking as into a multi-design approach where we take into account interaction, for example, between durability and seismic performance. Now, item number 6 is really application of the technology into bridge substructures. So can we design those sort of plastic hinges with this new high-tech damage control locking system? And the answer is yes. And what we have done in the last 6 years, we basically, thanks to the project funded by New Zealand Natural Hazard Platform, we basically went through a set of different type of bridge piers, hammerhead, and double pier band, and we target the low medium span bridges because that is what we have here in New Zealand. Mainly, we are talking about precast concrete decks, and these are sections that comes from the NZSEE research report. And I want just to show you 3 different type of approaches. One test that we did was basically we decided to say, okay, let's minimize the initial cost of when you go with this sort of structure. Let's have as a fuses internal bars, which are debonded for a certain length, and but have already in mind what is going to be the repairability. So what we have put pre-inserted threaded sockets, and we did the test. Then we cut the bars through, and then we post-installed axial devices that I will show you the details later. And we've done it in such a way that the moment capacity is pretty much the same, and we have the same ductility. In this way, we don't have to strengthen or redesign the foundation, which is very, very important. And as Stefano mentioned, if we talk about axial devices, we are pretty much talking about the bars which have been necked down, and I mean the first one at the top is a sort of mini BRBs. I know that this is the most Googled word probably in New Zealand at this stage. But we also developed dry dissipators, like where basically we don't put fillers between the tube and the bar, and these are grooved bar dissipators, as you can see in the middle one, and then we have. We are here at the point, and then we have a multi-fuse dissipator at the bottom. Very stable performance, and the actual devices work very well. We did more than 100 tests. We have papers published with design guidelines, and we also tested, for sake of curiosity, we also tested bidirectional loading on bridge piers, and we actually confirmed the device is working very well. I know that some researchers found some issues, but I think what the issues that they found because the detailing of the connection device was not properly detailed, and that is very important. Now, to consider. This is another solution where we decided to use couplers. Couplers are not allowed to be used in the plastic hinge areas, but what we did again, applying capacity design principle, we fused down these part, so we have a grooved section, and the idea is that after the earthquake, you accept to have a little bit of damage in the structural member, but we know how to do it. You see here, the couplers are all put with denso tape. After the first test, you remove the concrete, and then replace the couplers. Now, in this particular case, self-centering is crucial, because if you don't have a post-tensioning or anything, a rubber band which keeps, that brings the structure back to original position, what you're going to have, you are going to have a misalignment of the couplers. You're not going to do, and you're not be able to repair the structure after the earthquake. What we also tested, we tested the benchmark, the beginning, the solution, and then the repaired one. And we don't have time to go through the hysteresis, but the idea, the concept is to show that it is possible to implement it. And the key thing is to have a pre-planned repairing strategy when you design your structure. This is really critical if you want to have really a low damage structure. And then there's most obvious one, you've already seen some application. We tested the pier band. Also, I don't have time here to show you, but we also tested a monolithic type connection system to have a sort of benchmark. And again, when you have this sort of system, you can choose the device that you wish. And we came out with a sort of invented technologies, another new device, and we actually combine the devices together as well. And what I want to point out here, that we also use in this connection, we tend to have always shear keys in order to decouple the flexural capacity with the shear capacity. And you can see here, as I said, is a big crack developing at the bottom of the pier. Now, as also Stefano was pointing out, it's not either isolation and control rocking. We can even combine the technologies. And the idea is actually we could combine in a way that we create a sort of multi-level performance-based design. So basically we could have the devices activating in different performance levels such that we can increase the overall robustness of the structure. And one of the students, Royce, is going to do a big test, and we're basically going to have a rocking between the pier and the footing developing at ULS, and then we will activate a pure rocking at the bottom of the footing. So it's a combination of rocking and control rocking. Not sure if it works. I will tell you in 1 month. But let's move to item number 5. Now, can we also apply the technology in a bridge superstructure? This is a little bit less obvious, because you usually think, okay, when we design and think about superstructure, always think about seismic isolation, so the connection between the deck and the pier. And what we actually decided to do, actually to create a sort of control rocking system within the deck. And in reality, so again, the concept is very similar. We will have post-tensioning, we will have different sort of dissipators. But I think what I want to point out is actually that NZSEE started the seismic strengthening program 15 years ago, and they actually using linkages, sort of elements to actually, with a different philosophy, to keep all the bridge parts all together. And the concept here has been then tested on a large scale. This was the last test that we had in our extension lab. And these are the example of the devices that we placed in the deck. Now, what I want to point out, we tested the 2 configurations because we were targeting short video span bridges. And imagine you have a 20-25 meter span, and sometimes you can have a 4-lane bridge, which means you're going to have a 20-25 meter width. And so if you start having rocking of these elements, what's happening if you use this configuration, you're going to have a huge beam elongation developing within the deck, and if the abutment is locked in, you basically have a huge compression force developing in the deck. So what we actually decided to split the deck and to put U-flexural plates developing between the members. And again, this device was invented by Ivan Skinner. Now, because, as usual, running out of time, I want just to show the kinematics of this, one of the few tests that we did. So this is looking from above. This is, you can see, is the deck, which is rocking over the pier. Obviously, the pier is remaining elastic. And then the U-flexural plate, which is activated by the relative movement of of the deck. Okay, now item number 4 is Wigra-Madala Bridge link. So I want you to remember this bridge because I believe is the first one using this technology in New Zealand and probably in the world. And this bridge, I'm very happy because it's very close by to the university, which is here, is Christchurch, and therefore I can take students to have a look. Nothing special. If you look from outside, it looks like a conventional design. And the bridge was designed by Opus, and we were involved as a peer reviewer of the bridge. Now, what I want to mention is this, that the innovation was actually, I found actually in the way we achieved this bridge, because we launched the Canterbury Bridge Group in 2011. We had more than 20 seminars. We had more than 10 lab tours. And in this way, we was like tutoring and talking together between the Christchurch City Council, Opus, and the University of Canterbury. And at the end, what they wanted the Ferrari of bridges, the last model. And I think this was a great achievement, and the designer Peter Rutledge was really a great mind, and I will show you some details which I couldn't even think about. So the bridge is a typical conventional, let me go back, is a typical bridge, super T-beams, 35-meter span. There is a little bit of complexity, it's skew one side and flat on this side. And the footing was already designed actually by Becker. And so there was some constraint with the design of the footing because the capacity was already predetermined. And what basically the idea was is simply to create a control rocking mechanism developing top and bottom transversally, and then longitudinally the rocking is developing only at the bottom. And one requirement from the client was to have the dissipators not exposed, and that created huge challenges with the detailing. The dissipator is grooved, and is replaceable. We used here 50 millimeter McAlloy bar, was again another challenge to get the 50 millimeter McAlloy bar, but you can use tendon as an alternative option, and this is sectionable from the top. And I want just to go very quickly, if it goes. No, they say to press strongly, but it doesn't. Okay. Sorry, I got stuck. Oh, and one just snapshot. The nut was something that Peter came out, and that's is a particular nut that was in tension and compression, and this is the kinematic of the bridge. Now, if I'm not sure why it's not working, so I'm just pressing quite strongly, but it doesn't go ahead. So unless I crush I just, what should I do? Punch the, okay. So these are some details. We have internal shear keys. We use the bridge as a steel tube externally, and these are devices, the installation of devices. We put denso tape in, and then I can't really. And then this is the detail of the construction sequence. And I just want to mention that the pier band was cast in place, and then we used the super T-beams as a decking system. At the end, you will ask about cost. I will tell you the cost was around 200,000 more than a conventional design, over 8 million project. So, and overall, Hawkins was the contractor. They finished the project 6 weeks in advance. So if we move forward, this is bad because it's slowing down my time. Item number 3, design shift for reparability. And in the bridge manual, we have a sort of bonus. If you design, when you define your allowable ductility, you have robustness, redundancy, and predictability of behavior. And the question is, what about repairability? And I think this is a good question because we can say, can we design those structures maybe for higher ductility and still guarantee the maximal credible earthquake event performance? And I don't have time now because I only have 15 seconds. There will be a follow-up session, and Brandon is going to talk about this, if this is achievable. I also like fishing, as you can see here. Now, Item number 2, 45 seconds. What about resilience-based design? I think this is, and I start here with a question, are we ready for bridges? Because READY is an initiative, actually, I think driven by HARUP, where they're talking about a resilience earthquake design initiative. And I think when you look about resilience, it's about reducing the failure probability, reducing consequences from failures, and reduce time to recover. And all this brings to functionality. And what we are doing, we're actually working with another PhD, and she's going to present in a follow-up session. We're actually looking at developing recovery functions and on specific case studies in order to have a better way to communicate with the client what is really controlled damage, because it's all about being able to repair the structure in a very short time. And what I want to mention is that, as also Stefano mentioned, is that the future is actually to combine low damage technology with monitoring. And if we could have that embedded with cost-effective sensing, we could actually reduce quite a lot the recovery time. And the last one is an African proverb, very easy and short. If you want to go fast, go alone. If you want to go far, go together. And where are we? Halfway through, because we implemented the first bridge, but there's still a lot of work to do, because the main aim is actually to have possibly some guidance implemented in the bridge manual in order to have a more wider implementation nationally and worldwide. Thank you very much.
Thank you, Alessandro. That's the end of the Italian section.
Yeah.
And now foundations and geotechnical must be at least as important as structural, coming from a structural engineer. So now Professor Misko Cubrinovski is going from the University of Canterbury, is going to talk to us about the geotechnical perspectives for damage control in structures.
Thank you, David, and good afternoon, everyone. So I'm going to provide slightly different perspectives, I guess, about damage control in structures. Obviously, for that reason, I will provide a short background so that I set some context. And with one slide, I'm going to say something about damage control requirements, the way I see them. And then we'll focus really on structures on shallow foundations. There will be a couple of slides on piles to address the key domains of interest or influence, if you like. The first one is the immediate soil foundation interface. The second is the overall foundation soil beneath the structure, if you like, that affects components and the structure as a whole. And then the system response. And we'll end up with a very brief concluding remarks. So the principal focus in geotechnical earthquake engineering has been really around ground failures and large ground deformation, for obvious reason, because they were the most impacting in recent events. Over the past 10 years, however, performance-based design has been focusing on quantifying displacements and deformations, and in that process, also addressing uncertainties and effects on structures. We have to realize that there are significant complexities in this process. First of all, it's very difficult to characterize soils and sites, so that is not a trivial process. Soil behavior is very complex under dynamic loading, and you can anticipate a range of different types of behavior and phenomena occurring. And of course, there is a very complex dynamic interaction between the soil and the superstructure, and all of these are overloaded by uncertainties in the assessment. So when we are discussing damage control in structures, my view is something like this. In order to control the damage, we should be able to estimate the damage accurately. To estimate the damage accurately, you really need to understand what are the key mechanisms governing the deformation and producing the damage. For that, you need good models that will be able to quantify the deformations for the key mechanisms. And in all of this, you need to address the uncertainties in the assessment. So in summary, for me, damage control calls for a quantification of the seismic response and effectiveness of control mechanisms, while accounting for the uncertainties in loads, properties, behavior, and the models that we use. So it's quite a complex task. So let's now focus to some of the issues that are dealing directly with shallow or deep foundations. We can recognize several important domains of influence. So here is, the first two is the immediate interface zone between the foundation and the soil, in which the vibration of the superstructure and back and forth movement is going to induce some plastic deformation. We have to account for that interaction. The second domain is this foundation soil here. And obviously we are going to see what's happening there and how components or the structure can be affected by that. And finally, we have to understand that all of this is going to affect the system. So we need to understand how the whole system, the building, the foundation, and the soil is going to work together during the event. So I will say something about all these three independent mechanisms. And we'll start with the first one, and we'll focus on one mode of deformation. So 1 degree of freedom, we are considering rotation. At this interface, you can anticipate elastic rotation. There will be a potential uplift of the footing, and there will be plastic rotation, so significant plastic deformation in the immediate foundation soil. So we can put this together now into a single macro element and put those at the foundation level and model the effect of this interface on interaction in our seismic analysis. By the way, this is recent work done by Maximilian, who is sitting here in the audience. So one of the things that we would like to use this model for is to estimate the deformation of the structure while accounting for potential differential movements between different footings. So you need to model really the whole frame and account for nonlinearities in the superstructure in this model. And you can get I'm having the same famous problem. Can you move the slides for me? Thank you. So the model works reasonably well. You can see moment rotation diagram and settlement rotation diagram where the experiment and numerical simulation are shown. So we can largely predict what's happening in this model. Next, please. And obviously, in our analysis, there are different targets, but one target is to identify transient displacements as well as permanent deformations and displacements. And from a geotechnical perspective, which is also very important for structural engineers, is estimating settlements, both global and differential. So differential movements are obviously very important. Next, please. So I will stay now with this mechanism and present conceptually some ideas how to use the rocking mechanism at foundation level to reduce the damage in the superstructure. This is a work by Gazitas, Anastopoulos, and Pater, who have spent some attention on this particular problem. So here is a bridge pier conventionally designed, so you're having a very large footing that is going to produce reasonably small deformations there, and consequently you're having damage at the superstructure, at the base of the pier. If you reduce the size of the footing, then you will generate rocking of the whole structure, which in turn is going to induce some plastic deformation in the immediate foundation soil. This in turn is going to reduce the damage in the superstructure. So we have transferred the damage from the superstructure into the soil. And here is validation by a numerical analysis where you can see hinge created at the base of the pier here, whereas you're having a lot of red colors on the alternative design with smaller foundation size, which is producing rocking, where we're having a large plastic deformation. So clearly, you can dissipate some of the energy in the soil instead of the superstructure. Next, please. But there is a price to pay for this. And here is what Gazitas is saying, a potential price to pay. The residual angle and rotation and settlement may, rotation angle, pardon, and settlement may exceed the serviceability limit. So you're not really controlling the residual deformation, which could be excessive. So that is kind of not acceptable. So there have been few studies, next please, where the idea is, okay, what about replacing this immediate foundation soil? If the width of the foundation is B, you go to a depth B, which is the influence zone for bearing capacity problems, and you replace that with a ground or material that you can control so that you minimize deformations in the soil. And that works reasonably well. An alternative approach has been used by Bruce Cutter, where they've used the concrete pads beneath the footing so that you reduce the settlement. As you can see here, the settlement has been reduced from the initial levels there to much lower levels through the use of the pads. And in essence, out of two mechanisms, you're using only one. The rocking mechanism is dissipating energy through the rocking itself, which is repetitive, so cumulative effect is quite significant, and through the yielding of the soil. If you make the soil not to yield or dissipate energy, you're still using the first mechanism. So this is the idea behind that work. Next, please. So let's move now to the second domain, the foundation soil in the influence zone. I didn't know that I will have this kind of problem. I have a lot of animation in the slides. We have to realize that if this is not a rock or a very stiff soil, moderate size and large size earthquakes are going to induce nonlinearity in the soil here, in this foundation soil. This is really the zone of influence for this relatively large building. That means there is going to be a reduction in stiffness and strength in that soil, as indicated here. So the shear modulus is degrading during the shaking. And in many soils, pore pressures will be developing. So these two mechanisms are always there. So we have to understand that this is what is happening in our foundation soil, which is influencing the structure. Next, please. So here is one interesting case where the importance of this foundation soil is illustrated. This is a 10-story building, base isolated in liquefiable soils. It is on huge pile foundations, 2.5 meters in diameter, go about 30 meters long. And the owner was insisting to understand how the structure is going to perform during earthquakes. So seismic effective stress analysis was conducted, and you can see the results of the development of pore pressures for this structure, telling us what is happening in the case of no mitigation measures. And then an additional analysis was conducted where soil mixing walls were constructed in a grid to reduce the deformation in the soil and see how that is going to contribute to better performance of the structure. So key here is that we have to evaluate the system response. We have the superstructure, the base isolation, the foundation, the soil around, and ground improvement that is inside. You really need this kind of model to let you know what is happening with this system during actual excitation. And that feedback to the designer is of huge value. Now notice this. I did perform this analysis in 1996. And the implementation of this kind of analysis is really very slow. However, there is no replacement to this. This kind of analysis are providing very important feedback to the designer about how the system is going to perform under realistic events. So we have to stick to this further in the future. Next, please. There are few issues that will be always there, difficult to deal with. One is the spatial variability of soils. So here is a 6-story structure from Christchurch on shallow foundations. You can see isolated footings there, very weak tie beams, and very small footing there, in highly non-uniform ground condition with a very weak part, especially here, which resulted in large differential settlements of about 26 centimeters in this case. So this kind of variability, spatial variability of soils is always going to produce bias in the loading and in the response and consequence permanent ground deformation that you have to account for during the design. Here is another case for that kind of response when you have asymmetry or eccentricity in the stiffness and mass of the superstructure. This is another building that many people will recognize. This is a building in Christchurch. And the results you are seeing here is the difference in movement of 0.1 and 0.2. So significant differential movement and settlement. This is a result from analyses that were performed by John Bray and his students. So obviously, when designing to control damage in structures, we have to account for this details that I was talking about. What is happening at the interface zone between the footing and the soil? What is happening in the overall foundation influence zone? How the system is going to perform and respond during this kind of event, including the mechanisms that you're using for damage reduction. So that is going to be a significant factor in the choice of the foundations that you would like to use in order to achieve the target performance. Ground improvement is certainly a methodology that is used in geotechnical engineering to improve the performance. So I have to say a few words about that. There are various methods, and they are really used to reduce ground deformations. And most of them would achieve that. That does not necessarily mean that you would reduce damage in your superstructure. So here is one example from the 1995 Kobe earthquake, Oriental Hotel, a large structure on pile foundations. It is sitting on top of reclaimed land. Actually, the key walls go just around the three sides of this building. And the piles are quite robust, 2.5 meters in diameter, about 30 meters long. Reclaimed ground, so obviously liquefaction was a concern. So they decided to use deep cement mixing and created a grid, walls in a grid, which were protecting the piles and pretty much allowing to develop their lateral capacity so that the desired response was achieved. And indeed, liquefaction did not occur. There was no any evidence of serious liquefaction around the building. However, you can imagine that all of this energy now from your strengthened foundation soils, including robust piles, is vertically entering into the building, and it will dissipate into the building. So consequently, your damage to the structural elements and non-structural elements may increase. So clearly, this is a very important consideration. Again, pointing out that you can't consider these things in isolation. You have to check what's happening to the system response. And we were seeing that in Christchurch. This is now a case for the typical response of the bridges in Christchurch. We are having lateral spreading is pushing the abutments towards the bridge, which are then resisted by a very sturdy superstructure, which is developing a deck strutting mechanism. So abutments cannot move at that point, but they rotate around that point, and we have this inward rotation of the abutments with consequence push of piles and damage. Again, this is really a response defined by the particular system components that control the bridge deformations, and they include lateral spreading, which is the key demand, and the sturdy superstructure, which is enforcing no movement at certain point at the top of the structure. So, oops, this is now, I want to stay on the previous one, thank you. So damage control calls for quantification of the seismic response of key elements and the system as a whole. Thank you. So here are my concluding remarks, and I'm saving a little bit of time. They would appreciate that. For damage control in structures, we need to identify key mechanisms of deformation, and we need to quantify deformations and displacements. Next, please. In this process, we have to consider at least 3 domains of influence: the interface zone of the soil and the foundation, the overall foundation zone beneath the structure, which is the zone of influence that I call, and the system response. We have to consider independent elements as well as interactions between all these components that I've mentioned and 3 domains. And in that process, we have to consider all the uncertainties in the assessment. So I would just say that we've made very good progress in this regard, in developing better tools and procedures to address the issues. But I think we should do better, both in terms of developing better tools and processes to support the assessment as above. Thank you.
So the next presentation is a short one, 2 short ones at the end. So Dave McGuigan, who's the Deputy Chief Engineer at Ministry of Building, Innovation and Employment, is going to talk to us about the work that's going on the guideline for low damage design buildings. Dave. good luck with the remote control.
Thank you, David. I'll begin by acknowledging my co-author and the key facilitator of this project to date, Jeff Bird, and I'd also like to acknowledge the efforts of the members of the working group and reference groups who have assisted so far. A number of you are in this room. Looking at a few of the drivers behind this project, the Canterbury Earthquake Royal Commission made a number of recommendations with respect to low damage technologies. These included the government should foster greater communication and knowledge of the development of low damage technologies among building owners, designers, building consent authorities and the public. And the government, in conjunction with industry, should ensure evidence-based information is easily available to designers and building consent officials to enable low damage technologies to proceed more readily through the building consent process. A proposal by the Structural Engineering Society of New Zealand had also been developed, presenting the case for an industry-wide code of practice for low damage design, and this proposal was expressing concerns that some specified low damage structural systems being implemented were unproven and may offer little reduction in overall building damage. While the buildings with these low damage systems from a building regulator perspective should exceed the objectives of the building code, it is still very important from the regulator's perspective that there is a consistent approach to the design and consenting of these buildings, and therefore the development of a low damage guidance document to promote the uptake of these designs has been incorporated into the MB work program. The low damage systems will often be alternative solutions under the building code compliance framework. These will typically require consenting authorities to apply more scrutiny when checking these designs for compliance with the building code. It should also be recognised that conventional designs that follow the acceptable solutions and verification methods, such as the cited structural design standards, can also lead to low damage outcomes. It was also impressed upon me at a low damage workshop facilitated by Quake Corps earlier this week, when I gave a similar update on where this development of this document is at, that this document could well be better titled Low Structural Damage Design Guidance, as it may not be covering all the performance aspects of a building. For example, systems that focus exclusively on structural damage may be neglecting 75% of the building value. It is acknowledged that there is more work to do to ensure the message is clear and what is covered, and the title, including the words low damage, may well change with time. The objectives of the low damage guidance document are to facilitate communication between the various parties involved in the design process, particularly at the outset of a project when a building owner or developer may want to look at options that would best suit a project. The document will set out a standardised framework of performance objectives and performance assessment criteria that are clearly described. The document is intended to be freely available and to be performance-based and material system agnostic. It is also proposed to be the parent document to a potential suite of more specific low damage system documents, such as seismic isolation guidelines that Will Parker will soon talk about. The document is not intended to be a tome and is targeting a 50-page length. It is also anticipated to be endorsed as guidance to support the building code under Section 175 of the Building Act. The process to date has involved a number of reference group meetings. The first was held in October 2015 and the last in June 2016. The reference group has included practitioners, academics and representatives of the NZSEE and SESOC, and they have assisted with shaping the content and direction of the document. A literature review was also carried out early on in the process to see what similar documents exist and how they could be utilised for the development of this New Zealand-centric document. Between reference group meetings, a smaller core working group has been developing the content of the document, and this was continuing up until the 14th of November Kaikoura earthquake, when more urgent matters suddenly needed attending to. An overview of the contents of the document as they stand is now presented. The front end of the document is proposed to be high level, targeting an informed building professional on the overarching principles. The more technical aspects will be introduced in the sections on performance objectives and performance assessment criteria. It's proposed that the appendices include short summary pages on specific systems to provide illustrative examples to assist with when considering what system may best suit a certain application. Looking in more detail at the performance objectives as they stood, 3 key categories included safety, damage and recovery. And we introduced the continuum of limit states with serviceability limit state, damage control limit state and ultimate limit state. The current focus of development of the document, or where the process got to at November last year, is on a list of topic areas for discussion that should be used to initiate discussion in order to develop a reflected client brief. The proposed list of topic areas for discussions is shown in this slide. Once the specific topics are agreed on, the next step is to map these to performance criteria. An example of some of the performance assessment or structural design criteria, as they may be termed, are presented in the next slide. This is where it is proposed to introduce the more specific technical aspects such as acceleration or displacement limits, as well as considerations on access to elements for repair. The degree of quantification in this document is intended to be limited, and the more specific technical criteria is expected to reside in the specific guidance for individual low damage systems. So I hope you have an appreciation of where we are at with this project and what it is trying to achieve. Looking at the next steps in the process, we will hopefully soon get the working group going again to finalise a script document that can be presented to the reference group around the middle of this year. This should then point the way forward on what needs to be done to move from the developed script to a final product. When the document will be complete and ready for publication is certainly not clear right now, but I hope a year from now, at the time of the next NZSEE conference, we will be getting close to the end of the process. I reiterate that MBIE are committed to this. The challenge being faced, and is often the case, is achieving a document that is simple to understand and apply while still being appropriately robust. Thank you. That's all.
Thanks very much, Dave. So the final presentation in this session is by Will Parker from Opus International Consultants, and he's going to talk about the development of guidelines for the design of seismic isolation systems in buildings that is underway. Thank you, Will.
Hey, thanks, David. You'll see that David and I are co-leaders of this guideline, so when we get to questions, I'm sure David will share that. And I'd really like to just say that I'm talking on behalf of the group. So most of them are here, not all. So just a quick outline of what we're going to try and cover. Just a bit of background and some objectives. Dave's painted a good picture there. Just some of the challenges we've had along the way. There's been a lot, and I think there's still a few out there. We're making really good progress, so I'll give an update on that. I'm going to try and show a bit of the guideline. It's quite hard to do because it's like, how do you share a New Zealand standard and make that sound kind of interesting and palatable, but I'll do my best. And then just what we've got to do to get the thing finished and what might happen after that. So just by way of introduction, I think Dave's kind of introduced it big picture-wise in terms of Royal Commission, obviously uptake there of low damage. There was a lot of uptake of the technology in Christchurch after the quakes, so there's a lot more buildings down there, so a lot of people using the approach. So it was initiated by NZSEE a few conferences ago, and it's been really well supported by all the technical societies and mainly funded by MBIE and EQC, but big thanks to all the other societies as well, and it's being managed by the Quake Centre, who are just kind of keeping us corralled. So basically also there's no real adequate guidance in New Zealand, whereas it was the country that had invented it, or LRBs anyway. Sorry to the Italians, obviously, if you go back a lot further. And I guess in New Zealand there was certainly a lot of different approaches being used and different adoption of international standards as well. So I guess our main objectives were to kind of try and align what we were doing with clearly with 1170 and the building code, try to get the performance-based design in there, and also laterally align it with the low damage coded practice or guideline. And again, encourage the uptake of the technology. And then it was basically decided that it would be a guideline, but with a commentary and code type format. So not trying to make it too prescriptive, but providing a lot of guidance, information and commentary format. Okay, so I'm just going to try and keep it a bit light. So I thought, given that we're nearly there, we'll kind of give ourselves a mark as we go through. So just to kind of pick up on the main challenges. A big one was, what do we do beyond ULS? Obviously, overseas codes talk about MCE, and that was not really an easy topic for some of us in New Zealand. So we've managed to get there, and we've called a limit state called collapse avoidance limit state. So we've given I've actually put these scores in, so no offence to my fellow chapter authors. If you feel like you're getting a low score, we can deal with that later. It's really just to try to, it's certainly not personal, and it's really about, I guess, where we've seen the key challenges, and we've all had to input to make sure that we can get onto the same page, and that's been easier said than done. Even though it's been a fantastic group of people and a great intent, there's just a lot of devil in the detail, and a lot of different approaches have been used, so that's been a really good process to get through that. Consistency of approach with the isolation system itself and the superstructure, that was in some ways quite a biggie, some different things being done, and I think that's been really successful. There's been a really nice piece of work done by GNS on ground motions, looking at the longer periods. I would give that a 5, but I know getting a couple of seismologists to agree that would probably be a dangerous thing to do, so I've gone for 4.5. So to make it simple and cost effective, I think we've made a pretty good fist of that, but I know there's always a push for more, so I think there's room for improvement there, but we've tried hard. Again, I've probably been a little bit challenged, so I've applied the scores today after talking to and hearing some of the other speakers. So isolator variability, I've sort of kept that pretty low. Maybe that's a bit provocative, but and specification for supply, that is a biggie. And because we knew it was a biggie at the outset, we've kind of had a go at it, but really it needs more work. So picking up on Gian Mario's challenge, perhaps we'll come back to that at the end. So how have we treated it? I guess to deal with the ones that we've done quite well, I think we've had some really good ideas from various people in the group, and one was to try to define the types of buildings we're actually talking about, and that way we can kind of guide people into what they've got and make it a bit simpler. So we've got the 4 building types, and we've tried to make the simple one exactly that. You can use the simplest analytical approach, but it has to be a fairly regular structure. We've also got a design flow chart and a lookup table, so you can go to each type and you can find out how to go about it. We've defined the damage control limit state, so we've tried to bring in the performance-based design there, and collapse avoidance, as I've talked about, and the spectral work. Okay, so those are the chapters. They haven't really changed. We've moved things around between them, so I won't kind of dwell on that. I'll just move straight along. So just looking at chapter 2, which is kind of defining your how you're going to comply with the code and your philosophy. So that's where we define our 4 types. Just to give an example, that's type 1, so it kind of just defines what you need to comply with to be in that type. And the idea is to really make this simple so that people can get in there and not spend a lot of time on analysis, keep it real simple, and still get a really good result. So I won't read through each thing. I guess the key thing there is this is going to put some limits on aspect ratio, plan size, controlling uplift, that sort of thing, and then a simple approach works fine. So then I guess this just brings in the kind of the performance aspect, is the looking at the collapse avoidance limit state. So what we've tried to do there is basically say, okay, when we're looking at that limit state, how conservative are we going to be? And this came about from looking at the different types of structures, where you put the isolation plane, and effectively what is your level of robustness beyond ULS. So what we've defined there as a good building, or one with good rattle space around it, you get a 1.2 factor, which is a high resilience, so it effectively reduces your hazard. If you have a reduced resilience at your rattle space, so for instance, if you've got a bearing on top of a column where you could drop a significant distance vertically without some other sort of restraint, then you just have a 1 factor, so effectively you get a relatively higher hazard. Okay, looking at performance, just picking up from Dave's comment, what we've tried to do there is actually define, as I've said, the damage control limit state. We haven't prescribed what the return period is for that, because this is a performance issue to talk about with the client, but we have set some kind of performance measures. Some of them are more big picture around those limit states, but we've just tried to define some here for damage control limit state. So it does go beyond the structure, it does talk about secondary structure, and in this one it talks about shelving. This is just an example, but it's a thought provoker. It's something that should be included in your design effort. Okay, sorry, I realised I had one of my slides out of order, probably my resilience factor, but kind of goes with this. So coming out of the hazard, this is just looking out to the longer periods. So if you have a look here, I'll just try my pointer. Oops, sorry. Where's the pointer now? Have I got one? No, I haven't. Okay, that's all right. So if you look at the solid line, that is the 3 second. If you look at the dash line, that's 5 second. So that's quite relevant for some of the more flexible isolators that you can get. So you can see there, just looking at those displacements, what a difference that makes. And the dotted line, the fine dotted line going right out, that's 10 seconds. So we don't really expect to get there, but that's, I guess, just to show where GNS have taken the thing out to. Okay, so just coming back to the design chapter and looking at type 1 again. So this is, there's a table like this for each section of the building. So one for the isolation plane in this case, there's one for the superstructure, and there's one for the substructure. And there's one effectively for each of the limit states that you need to check. So it's pretty helpful in terms of guiding you through it. So just to take the 1.5 down there, it basically says you to go about with a simple method how to look at your displacement ADRS spectra, which you can develop from what's in the guideline. And then there's a reference there that actually refers you to some equations, which in this case are taken from NZSEE 7 to check some of the properties that you're still complying. So this is when you get into the detailed design. Okay, so just an update on progress. We're actually getting pretty close. We've got a draft document together. We've sent it to four plus international reviewers. 3 of them are in the room, 3 or 4 of them are in the room. So it's really great to be able to have. We're trying to organise a sort of a discussion on the fly while those people are together. But that's all being collated. We've got a spreadsheet which basically captures their comments, everybody's comments, and then what we're going to do about them, so we can send the spreadsheet back to them so they can understand what changes we've made to incorporate their feedback. Then we just need to finalise the document and publish it, make it available as a working draft, and we really encourage everybody to have a look at it, hopefully use it, and provide feedback, and then we can continue to improve it. Then there'll be some training that comes as well, and make sure that document gets disseminated. So I guess I give ourselves an overall report of sort of 3.5 out of 5. I think it's a good effort. I think we could be criticised for making it too broad because we've tried to make it kind of so that you can adopt. It's not too prescriptive. I guess picking up again Gian Mario's comment, it's not telling you exactly how to do it, but we've captured a lot of information in the commentary in particular, which should provide a lot more understanding and reasons why approaches are there and why they're not there. So, or why we don't recommend some things, rather than just saying do this. It actually says, well, this is what we think you should do because of this and this. So again, if you can build an argument and bring your peer review with you, but it should provide a simple path as well when you don't want to have to go down something too challenging. And I guess the key challenge that we're picking up there is to probably improve some guidance on bearing variability and also testing for those of you who have been to some of those presentations today. So I just thank everybody, particularly to our sponsors and all the stakeholders and those who have inputted to the document, the really talented and really committed group that I've been working with, and also the support we've had from QC to help us keep us on the straight and narrow, and those peer reviewers. Thanks a lot. So do you want me to start off with a question, David? Because I know I think there's a few there, but I was going to just pose one, and there's another obvious one, but I guess it's we pretty much settled on this, and then we kind of thought, well, maybe we're actually being too conservative. We've actually, we've got a collapse avoidance limit state, and you could argue we're already putting a margin on that with our resilience factor, or if we don't have one. So we're trying to scale back our factor up to effectively what is collapse avoidance. And I guess the question that I want to pose is, in the US, as you're probably aware or have heard today, that they pretty much have a blanket MCE of 1 and 2.5 thousand year return period earthquake, whereas we're very much governed by our importance levels. So what we're suggesting is that we scale that back. For an importance level 2, we have a higher factor and a lower for importance level 4. So I guess I would just invite people to jump up and make comment on that. Should we have a blanket MCE, or should it be importance level dependent? Do you want to take over from here, David?
Go back to the question answering.
All right.
May I? Is this on? Yeah.
Yes.
David Hopkins, consulting engineer. I just want to compliment the organisers and the presenters for a particularly stimulating and informative session. I'm not actually going to address your comment, Will. Just a couple of, as usual, the stimulating presentations sort of filled my mind with lots of things. Two really, really important things kept occurring to me as we went through this resilience, low damage type factors. The first is a word I'd like you all to remember, and it's QuakeStar. QuakeStar, you will know, is something I've been working on. It is an assessment system for New Zealand buildings which looks at safety, damage and repair time. It has the potential to do two major things. One is to remind engineers of these other dimensions of the way we design things. Even more important, it has the very strong potential of raising awareness in the marketplace to drive the market to actually ask for the things that we've been hearing about. That's the first point, QuakeStar. The second point is tolerable impact tables. In 2007 and in 2011, 12 and 13, within Department of Building and Housing and MB, we developed the start of what we call tolerable impact tables, which were really a matrix of performance, rather like the one that Stefano showed, except drilling down into performance requirements. One of the things that struck me from the low damage document and the seismic isolation document is we've now got two sort of tables of performance criteria. These tolerable impact tables that we developed within DBH MB were actually across the board. And it strikes me that the low damage and the base isolation really should be we should be developing this broader table and using, and from the base isolation and the low damage design, looking at those and choosing the ones that we are seeking to comply with for each of those, rather than developing ad hoc, if you like. It's not a criticism, it's just an encouragement to maybe make sure it's all integrated across the board. Thank you.
Thanks, David. I could probably have a go at answering that. We understand that, and I think we need to converge what those performance objectives and criteria are, what the tolerable impacts are. That we're all talking about the same thing, so we do need to standardise the approach and the language and the terminology. So it will apply to everything. I want to just take control here. Thank you to the speakers for leaving a little bit of time at the end. I wanted to ask them a question, though, which really relates to the topic of Stefano's presentation about, is it possible? Do we actually think it's possible to design an earthquake-proof building? And I would like them all to sort of to answer that in one sentence, if possible. Yes, no, maybe, or yes, but, or something. Can I just ask them all to answer that question? Because I got interviewed a couple of days ago and the media got very excited about this terminology of earthquake-proof buildings. And I said, we're very reluctant to use those terms because we say it can't be done. But actually, some of the people who will be at this conference will say it can be done. And so I would really just like to ask you all a simple question. Could we design an earthquake-proof building?
Okay, go, thank you. Times ago, quick and fast, someone was asking about whatever, and I mentioned that when I was a kid, I remember a great presentation at primary school about the fast magnetic train, the bullet train using magnetic fields. And thinking that not in our generation, but in the future, 150 years, 100 years, but yes, it is going to happen. That's how I hope is going to be the science fiction of earthquake engineering, that we are going to have a triggered earthquake. There will be enough seconds, just a few instances, sufficient enough to lift up magnetically or whatever else will be the power in the future to lift up the building, completely disconnected and come down. And people will be laughing. Do you know that there is an harvesting, energy harvesting, a lot of work going on that? So now just imagine that in the energy harvesting approach, in 50 years from now, 70 years from now, the movement of the earth close by to the building could be possibly, why not, being used as an energy to actually give us that magnetic field. So my answer is yes, but not now. So we need to make sure that people are aware that it's not an earthquake-proof building what we can deliver. And even base isolation is not earthquake-proof. It can be a 6-star rating or a 6-, but it's not yet there.
Okay.
Stop.
Well, that was a long sentence.
Yeah, hi, David, thanks. I think I have a similar answer, so I'd say from what I've heard this week as well, there's some systems out there for dealing with vertical effects. While we've got some big hazards, say off the locked up section of plate out east, what's that going to give us in terms of vertical effects? So I think, yeah, just saying because you've got isolation, you're there, you're not. So I think, yeah, we need to probably better understand, but I guess if you look down Chile, they're pretty much dealing with their MCE on a daily basis, so what could they get that's bigger? And I think we're right, if we can deal with the vertical effects and effectively make sure we know what our MCE is, we can get there, but we're not there yet.
Thank you. Misko, would you like to?
I would say probably the answer is yes, but I would ask the question, do we really need it? You have to put it in the context of society, and I believe we don't need earthquake-proof buildings everywhere around us, because that would mean significant effort and expenditure that is going to be unbalanced regarding where the world is right now. So in that sense, I think the challenge for engineers will still remain to be to provide means and tools that we are good at to address society needs the best we can. And in some cases, we will have earthquake-proof buildings, but they will be isolated cases, I would say, for some time to come. So we better look in other methods as well.
Thank you. Alessandro.
I will be very quick. I'm just probably shifting more on the bridge perspective, and I think obviously my answer is probably a maybe, and simply because again, if you think about a bridge, there is the geotechnical component, which is huge and important. And even in the way Misko was presenting the approach of control damage, there is a different way of approaching and interpreting control damage. And this means that depending on the soil conditions, you will have to find a solution which is still robust, but maybe it's not a bridge-proof structure. So it's a maybe depending on the condition that you have.
Okay.
We don't have to push for any type of structure. That is my answer.
Thank you. Felice.
I think the only solution at the moment could be the base isolation, improved, considering also the possibility to have movement, larger movement than now, because now we have the limitation of the characteristic of the devices, but I think is the only at the moment the only solution to have the very proof seismic building.
Okay, and what does the regulator have to say?
We didn't define earthquake-proof, but I'm going to say no.
Okay, and there's at least one other person in the room who I'd like his opinion on, and that's Rene Lagos. And if anyone else would like to give theirs, please stand up.
Yesterday I expressed my personal opinion, and I think we already have the knowledge and the technology available to have proof buildings, earthquake-proof buildings. Anyone that has taken a look at what has happened to base-isolated buildings in some of the strongest earthquakes would realize that it's a very, very safe alternative. And what we have realized, it is also very cost-effective. I mean, it's not prohibited value. Most of the countries should be aware that the money they have to spend in repairing and the social implications of damage are a lot more high than putting a few dollars per square meter just to add this kind of technology. So I think it's the challenge that we face as structural engineers. We have to put those technologies to work as soon as possible. Maybe put it somehow into the codes, I don't know. It's strategy that, but the knowledge and the technology is already there. Thank you.
Thank you. Would anyone else like to give a comment? Yes. Two.
I do wonder what the consequences are if we start advertising earthquake-proof buildings and then we get an earthquake that inevitably does significant or perhaps catastrophic damage to one of these buildings. I guess the follow-on question from that is, what are we trying to achieve by using the term earthquake-proof? Are we trying to give society a greater level of insurance in what we're providing them? Is it a simple messaging system? And then inevitably, the pessimist in me says, when something does go wrong, how do we deal with that?
Thank you. And I think we have Jitendra.
Okay. I think I agree very much with what earlier told by Craig and Misko. Do we really need it? That's one question. And then what is the assurance when we say earthquake proof, it will be really earthquake proof when we don't know how big the earthquake will be. Because earthquake is not in our control. We can design a system which is in our control. So how we guarantee it will be earthquake proof? Because there's always uncertainty, and that will give a wrong hope to the society. So I don't think we should be using a term earthquake proof. Thank you.
Okay. And Peter. Graham first.
I've got is I think that perhaps we can design a building to be earthquake proof for a given specification of ground motions. I think we've still got a huge amount to learn about just how strong ground motions might be. When I started my career, we thought our centro was strong. Now it would be regarded as sort of relatively weak. We've had near-fault motions come along. We're only just starting to learn about sort of the duration and strength, particularly at long period, that we might get out of great subduction zone earthquakes. So I think we're still a little way off even knowing what we should be designing for, let alone doing the design.
Okay, thank you. And the last comment from Peter Wood.
I've got two quick points. The first one, the goal of an earthquake-proof building can be there, but to try and suggest it can be delivered in the foreseeable future has to be resisted significantly. I have one detailed comment that relates, and that's the reference to importance levels. Why do we have different importance levels? I would understand that that is an economic factor in the design. I'm also very conscious that when you change the use of a building, the importance level might be inappropriate, but it's still the same building. Be careful.
Thank you. I think the consensus is that we should not use this term earthquake-proof yet, but it's a still a desirable thing that we're aspiring to. Look, I'd just like to thank all of the speakers very much, and we're now out of time, so I'm going to call the session to a close. We have a little gift for each of them, so if you could all make your way past me this way, and could everyone thank them all, please?